Bonjour tout le monde. Donc, le séminaire aujourd'hui sera présenté par Dr Mouhamed Dieye. Mouhamed a fait sa maîtrise ici à l'UQAM, au département, et aussi son doctorat. Il a soutenu son doctorat en 2023 et il est présentement postdoc à l'Université de Concordia. Donc, aujourd'hui, il va nous présenter des travaux reliés à l'intelligence dans le réseau. Et donc, je vais lui laisser la main. Merci.
Je vais présenter en anglais. Thank you very much. So I'll be presenting this series of work related to in-network computing in the network. So here I selected just about 3 works that we did in the last few years, the last 2 years, with regards to in-network computing. So let's start by just a quick example. So a few years ago, Mark Zuckerberg, So a few years ago, Mark Zuckerberg had a vision, and the vision was that metaverse was going to be the holy grail of social experience. So he put a lot of money on this, so about 10 billion investment in 2021. So now the conservative estimate is about 20 billion in 2023. So it is not a problem of investment. So he put a lot of money on this. He rebranded from Facebook to Meta. So he acquired some companies, so notably Oculus, which is now in the Quest VR headsets. He did a lot of software investment, so he tried to create a Meta Horizon Worlds, which is a social VR, a metaverse world, where the goal was to have user interaction and content creation. So it was supposed to be the next Facebook. So he created even peripheral companies, so the Novi digital wallet for the transaction, virtual workplace solutions for meetings and collaboration. So he really did he really gave a lot of effort in order to make this dream come true. Unfortunately, in 2022, he presented this. So this image was quite famous around the internet. It was supposed to be the metaverse that he invested a lot of money. So here is just a sample of the headlines that we had. So one journalist called it a stupid selfie. Another one called it selfie so bad, people can't believe it's real. So this was really, really famous, right? For a rare occasion, I believe this was an unfair criticism, right? So I believe that Mark did what he could because there are a lot of technical and technological hurdles for the metaverse for the current networks that we have. So we're going to see some of the technical hurdles that we have for the metaverse. So the big question is the metaverse a 5G or the current network application? So when we talk about the metaverse, here are some components: the virtual environment, which has to be highly detailed and interactive. So he failed on this. It needed to be a real-time interaction. So we needed synchronous interaction. The words need to be persistent. So if you quit the application, you should be able to continue where you were. And it needs to be integrated with the physical world, right? So these are the main components. And we'll see if we can actually have this metaverse in the 5G or the current networks. So one thing that we can do is just to look at the requirements for the metaverse, right? Or for the immersive applications, right? So here in the literature, we can see actually, so here, this is a figure on the bandwidth requirements. So from HD video to hologram. right? So here we can see when for the HD we needed 1 to 5 megabits per second in terms of data rate. For the hologram, to transmit hologram, the requirement goes about 100 gigabytes to 2 terabytes per second here, right? So we have a lot of data that we need to transmit continuously. We need to process this data. We need to render it, and we need to do this in milliseconds, right? And we need to do this also for millions of simultaneous users, and each user will have their own viewpoint, right? So this is extremely complex in terms of bandwidth and in terms of data rate that we need to ensure here, right? So here, a quick example is for just a 1 frame, right, per second at 30 frame per second here. At 30 frame per second for the Microsoft Kinect, we have 2 gigabytes, right, of raw data that is transmitted into the network. So this is a lot of data that we are transmitting for a small piece of data here, right? So here, this increases with the sensors, the viewpoints, the resolution, the frame rate, etc. Right? So we have a work that actually shows this also. So in terms of the latency, so here a clear threshold is 20 millisecond latency, right? So we need this because we want to avoid simulator sickness. There's other terms that use. Essentially, when you use head-mounted display, you want the latency to be less than 20 milliseconds because you're going to have some sickness, right, if you don't. But ideally, we want this to be as close to real time as possible, right? Because if it's not less than 20 milliseconds, you will not have the immersiveness, right? You won't feel that you are in the game, right? So if you take an example of the multiplayer game, so the latency is very important, right? So imagine you were playing, I don't know, any game. So if there's a high latency, actually, the players will feel it, right? The delay will disrupt the gameplay and will create this disadvantage, right? You have the same requirements for virtual concerts, really any kind of application that requires full immersiveness. So another key requirement is the synchronization requirement. So here you need to manage a lot of data that are coming from everywhere. You have objects that are coming at different angles. You need to sometimes do some volumetric fusion. So you need to fuse some object in order to create another object, right? So like any kind of moving media, it's unacceptable for frames to be slightly ahead or slightly behind, right? Because you will see this, right? So here we have an image where the image is slightly desynchronized here. And you see here, the rendered image is not good, right? So this is the image that we should have, and this is the image that we have because of the slight desynchronization. So here, the key word is we don't have to be just in time, it has to be right on time, right? We need to have the objects right on time in order to do a good composition here. So coming back to our question, is the metaverse a 5G or current network application? And the answer is most likely not, right? We won't have a good metaverse universe maybe with the 5G, right? So here are some considerations. It's very compute heavy. It requires synchronicity. We need low latency, less than 20 milliseconds. And we have to do this on an infrastructure that is fundamentally designed for asynchronous communication, right? So the internet that we have does not take this kind of application into account, right? We have to travel long distances through complex topologies. We have to take into account variable traffic, congestion, etc., right? So for many reasons, actually, the 5G is not suitable for the metaverse, right? So here the partial conclusion is most likely the metaverse is a 6G or a future network application, right? So now the question is, how can we ensure the metaverse in this for the 6G? So this is a work that is well cited by Walid Saad, and he explained the tenets for 6G, right? So according to him, for the 6G, there are going to be some driving applications. So here he presents a few applications that he thinks is going to be in the 6G. So for us, the metaverse and the immersive application can be classified in the multi-sensory extended reality application. So that's fine. So for the driving trends, he sees a lot of trends. One of the driving trends is the end of the smartphone era, right? So we don't only consider that the end point for the user is going to be the smartphone, right? It can be the headset, right? The head-mounted set. It can be any kind of device that can do immersive applications here, right? So he thinks that there will be a convergence of communication, sensing, control, localization, and computing. So we agree on that also. He believes that we need more bits, the spectrum, and more reliability. That's fine also. So here, for the last part, he thinks that there are some enabling technology, right? In our case, we believe that one of the enabling technology that is not cited here is in network computing, right? And so we're going to talk about in-network computing because we believe that in-network computing can be a key enabling technology for 6G. So what is in-network computing? So typically, when we do computation in the network, so we do it generally outside of the network domain. So typically, if you have the edge, if you have the cloud, etc., you're going to have the one endpoint here, and you're going to traverse the topology, so the connected routers and switches, and then you're going to go to a control layer where the servers will be. So whether it's the cloud or the fog, etc., there will be servers that are considered outside of the network domain. So the in-network computing just changes this a little bit. So instead of just using the switches and the router just to do transmission of data, we can do computing, small computing tasks on the network devices. So it will be small computing tasks on the switches and the routers, which are programmable, right? So we can change the task that we need to do based on the end user, based on the location, based on the network state, etc., right? So instead of computing on the servers that are located outside of the network domain, we are going to be computing inside the network. So what kind of devices? It can be switches and routers, FPGAs, etc. So we can have a lot of devices that can do a smart part of the computation here. So we were able to do this by executing code on the data plane instead of the control plane exclusively. And we're using now a high-level programming language, such as P4. There are some other programming languages available, but P4 is the standard for now for in-network computing. So if you've been in networks for a long time, you know that this is not something new. This is nothing innovative. We had something similar in the 1990s for the active networks. But in the 1990s, we were limited to very simple tasks. And we quickly forgot about it, right? But now there's a resurgence of in-network computing, mainly due to advancement in the data plane programmability. So essentially, we have better devices and we have better languages that we can use, right? So we have SDN that allows us to do programmability in the network. So now we've added a high level of programming language, as is P4, and the devices are better. So now we can do it, right? So a well-cited paper just summarized in network computing as a dumb idea whose time has come. So it's essentially something that we knew how to do. the driving principle to network computing. So there's proximity to data. So we're trying to process data near its source within the network. So we have a result that shows the importance of this processing near the source near the source within the network. And so this allows us to reduce latency and optimize bandwidth. So this is nothing new, right? We know this with edge, we know this with fog computing, etc. So computing near the source always enables us to reduce the latency. Right? So something that maybe is more interesting in network computing is the distributed processing. Right? We don't need to do the processing task on the server or centralized infrastructure. We can distribute it across the networking. Right? So this allows us to have a bit more of a scalability. It allows us to do some load balancing and fault tolerance here. So of course, with languages such as P4, now we have better programmability and flexibility. So we can dynamically configure the tasks that the network devices can do and customize these network devices to be adaptable to changing network requirements. So we can be more dynamic within the network here. So of course, because of the previous principle, now we can do better resource optimization. So here we are looking into energy efficiency, which is a key aspect in nowadays. So we are looking into energy efficiency processing within the network. We are also looking at automation in intelligent networks. So since it's not a dumb device anymore, the switch or the router is not a dumb device anymore, we can program some high-level stuff on these devices. Now we can increase the intelligence within the network here. So there are some work that try to explore machine learning algorithms where you can adjust the routing path based on the traffic pattern. And you don't have to go to a centralized infrastructure. You can do it in a distributed manner. So in our case, we're just going to present 3 works that we did in recent years. So we have the first work, which provided an architecture proof of concept. So we also have a work by Manel, which has been recently published. So Manel maybe next time can present this work more in detail. And also we have an architectural proposal also for the management of network computing components here. So for the first work, it's called an architecture for provisioning network computing enabled slices for holographic application in next generation networks. So we talked about the metaverse. Now we're going to generalize a little bit. We're going to talk now about immersive applications, so holographic application, AR, VR, etc. We're just going to consider this as a big family, and we're going to work on this family in our papers. So for the context of this work, so we consider holographic applications. So it can be holographic concert, holographic learning, holographic surgery, telesurgery, whatever. All of these applications share essentially the same QoS requirement, which is ultra low latency and high bandwidth, right? We already talked about this, so we're going to go quickly on this, right? So we know that the traditional network architecture is not sufficient. We cannot meet these requirements in a sufficient manner. So here, for this proof of concept, we just wanted to test if the promise is real. So we propose INC as a solution, and the goal is to distribute the computation across the network, right? So instead of relying on the edge or the cloud servers, we're just going to rely on the devices that are within the network here. So here, for the objective of this proof of concept is just to propose an architecture and test this proposal and see what are the results. So here we have the proposed architecture. So here at the bottom, you have the data plane. So you have the data plane with the programmable devices that we can control using P4. And then you have the control plane layer where the SDN controlling is. So for us, we just added these two layers. So we have an adapter layer. So you're not going to have the same devices across the network. Heterogeneity is a feature of in-network computing, right? You have to take those into account. So for this, we have an adapter layer. So the adapter layer, essentially what it does is just translate the commands that we have for the specific devices. And here we have the embedding layer. So the embedding layer essentially is going to be the orchestrator. So the orchestrator here is just going to decide where the resources and how many resources should we allocate for a specific slice here. Right? And this embedding layer is also going to deploy these INC program on the network switches, the network devices. Yes.
So adapter like
No, so adapter here is sort of a program. So basically for each device, we're going to look what kind of command can we send directly to the devices, right? So here we have high-level commands. So here maybe you have a Cisco router, or maybe a Juniper or a Huawei router. So these devices will receive different types of commands, right? Because they are different. And so the adapter is just selecting which command to send to which device, essentially. So for the workflow, so we assume that there's a holographic application provider that's going to submit a slice request, right? And we're going to specify the QoS requirements. We're going to say, hey, here, for this proof of concept, we consider it a holographic concert. So here we have the latency as requirement, the bandwidth, and the audience size essentially as requirements here. So the slice embedding service is going to analyze the network resources. So it's going to look at each network device. Is it busy? Does it have enough capacity? Does it have enough storage or computing capacity? And we're going to decide where should we place this function here that we need. Right? So we map the slice onto the physical network services. So we're going to allocate the bandwidth, the computing resources that we need on the devices that we've identified. So here for our proof of concept, we only selected one function, so which is the transcoding. Essentially, we're going to just place transcoding function within the network. And here we want to see if we can do a good job of placing this function, and does this transcoding allow us to reduce the bandwidth consumed here. So for the setup, we use Mininet emulators to create some sort of test bed. So here we have the data plane. So here we have some devices that are simulated in Mininet. So the goal is to place some transcoding functions across some of the devices here, and in order to reduce the bandwidth consumed here. Right? So here we have the other layers that we talked about earlier. So here we have the holographic concert. We go through a streaming server. So here we have some servers here because we're going to test out different scenarios. So we're going to assume that there's an edge server just close to the holographic streaming server. We're going to assume another scenario where there's an edge server just near the end users. We're going to assume that the users are distributed across the network here. And so here we're going to test out and see what are the benefits of network computing and does it really work, right? So here we have 11 P4 enabled programmable switches, right? And it's controlled by an SDN controlled network. We have 5 hosts that will act for us as the audience member that will receive the holographic stream. And the source is going to be the holographic console provider. That's okay. So for the scenarios, so we have three types of scenarios. So we have the transcoding at the edge, where we do transcoding at the edge here. So either this one or this one, and we transmit the data, or we transmit the data and we do the transcoding near the end users. So when we say EC1 is the edge server that is located near the end users here, when we say EC2 is the edge server that is located in the holographic streaming server here. So we have the transcoding at the host. So we're going to transmit all the data towards the end user and try to do transcoding at the end user location. Of course, the one that we're looking forward to evaluate is the transcoding inside the network. So we're just going to send the data here, and along the path to the end user, we're going to do transcoding using the network devices. So we have here some results here. So here we have when we use the edge computing near the end user. So here, quite naturally, we have very high latency, right? Because we're transmitting a lot of data, so uncompressed data across the network, and trying to do the transcoding near the end users. So naturally, this will cause a very high latency. So here, the best option is going to be if we do the in-network computing, or if we use the edge computing near the streaming server. So here, these are the best options. So clearly, the in-network computing works. So we're going to show a video that actually shows this in real time here. So from a load standpoint, so here it confirms the previous result that the in-network computing or doing edge computing near the end user is the best option, right? So trying to do either the edge computing near so edge computing near the streaming server. So if you try to do edge computing near the end user, you will have a very high network load here. And this is normal because you're transmitting uncompressed data across the network. So small conclusion from our result is that the network computing reduced network congestion by around 50% here. So I can show this in a video that we had for our demo. So here, essentially, we just run our simulations. So here it's going to be on Mininet with BMV2 for the P4 devices. So we're going to be able to use a P4 programming language here. So here, this is just setting up the programs here. And here in our scenario, so we didn't do the metaverse, but we use a 360 video just to do the comparison. So essentially the big idea here is we're going to use a lot of resources and we see whether in-network computing has some real benefits here. So here on the left, you have the video without in-network computing enabled, and here you have in-network computing enabled on this side, right? So here you can see that both video will have similar quality. So here, without the in-network computing and the in-network computing, so it has no impact on the user experience. So we're just going to look at the network load here between without in-network computing and with in-network computing here. So I'm going to skip a bit here. So here for the same video here, So you can see here that the network load is around 75 and 50 here, but here is less than 25%, right, of the resources being used. Right? So it's the same topology, it's just that here we activate it in network computing and here we didn't activate it. So here the result is clear. Right? The network load can be reduced significantly with in-network computing. So we're going to stop this video and continue. So some partial conclusions based on this earlier work. So the proof of concept confirmed what we suspected, that the in-network computing can have very real impact in terms of latency and bandwidth consumption. But however, you will note that we only implemented one type of function, which is the transcoding, right? So the thing is that we don't think that network computing should be used every time. So it depends on the task that you have to do in the network. The reasons are obvious. So the networking device still have limitations in terms of computation and storage power if you compare it to a server that is on the edge. So sometimes the network device doesn't have just the power to do the task that you want. So because of this, we abandoned the INC alone approach, and we believe that we can have a hybrid approach where INC becomes part of the infrastructure. So either in the infrastructure by combining with the edge or the cloud, or by combining the service composition itself. So instead of having just VNF, we will have VNF and in-network computing components, right? So that's how we will create future services. So some function will be exclusively in network computing and some function will be exclusively VNF. So for this work, we're going to be doing the first hybrid approach, which is that we will have an infrastructure where we have the edge and the cloud, and then we put into this infrastructure in network computing enable devices here. So this is a work done by Manel, which is called 3C resource allocation for next generation application in an in-network computing enabled edge cloud continuum. So it's going to be the same context and the same objectives, essentially. So we have immersive application in like the metaverse. And these applications demand ultra low latency, high bandwidth. So here we set a strict threshold, which is the 22 millisecond threshold for the latency. So that's our goal now. The high bandwidth, which is going to be more than 10 gigabit per second, high data rate. And here we have a high frame refresh rate, and we want to ensure at least 90 frames per second minimum here. Right? So again, same conclusion, the traditional edge cloud or fog cloud, etc., just cannot meet these demands here. So the solution that we are advocating is a 3C resource allocation model. So 3C means communication, caching, and computing within in-network computing enabled edge cloud continuum. So for the communication, essentially what we're saying is we want to optimize the data transfer path to reduce the delays. For the caching, we want to store digital assets at optimal location in order to retrieve them quickly. So this also impacts the latency, the global latency that we're going to have. And the computing is to process the workloads at the network nodes, right? At the optimal network nodes, instead of using centralized cloud servers here. We consider this system model. So we have the end user here with the head mounted display. So here you have this user is connected to an immersive application provider, and the goal of the application provider is just to send some requests and would set the QoS requirements here, right? And so the requests are going to need some real-time rendering, encoding, caching, and transmission of the 3D asset in order to compose the virtual world that we need. So here, the main component is going to be the resource allocation manager. So the resource allocation manager is the interface between the request and the infrastructure here. So it's going to analyze the needs of this request and see where should we place it optimally in the infrastructure. Right, so we have two main tasks to determine the optimal placement of computing and caching function, and dynamically to assign the workloads to the in-network computing devices. So the workflow here is very simple. The user will send a service request. And so this service request will have latency constraints, computation constraint, and caching constraints, or essentially some storage constraints here, right? The resource allocation manager will determine the optimal location for the 3C, so the computing, the caching. So the computing, the caching, and if I remember correctly, and the communication. So essentially what it needs to do is just to decide whether the task should be in the cloud or the edge or within the network, within the in-network enabled devices. So for the digital assets, so we need to cache them optimally. So we need to know whether we should also store it in the cloud, in the edge, or within the in-network enabled devices. So this is based on the user location and on demand. Right. So the goal here is to reduce the delay and improve content delivery speeds. So here we compare in this work two main algorithms. So here the main algorithm is going to be a PSO, which is a swarm optimization. And then we compare it to a greedy algorithm here that is focused on capacity. So here we're going to look for high capacity nodes, and we're going to try to place the functions there. So we formulated this problem as a mixed integer nonlinear problem. So here we have a few constraints. So we have constraints on the processing capacity, so we cannot exceed the vCPU and the RAM capacity of the nodes. We have bandwidth availability constraints. We have storage constraints, and we also need to satisfy the QoS requirements. So essentially the latency and the refresh rate that we require here. So the two variables that we are going to play with is just going to be the service function chain, so the function placement, and where we are going to cache the digital assets here. Okay. So here the goal is to optimize the computing, the caching, and the communication while minimizing the delay and the cost. So these are the two hard constraints that we need to satisfy in this problem. So here we have the algorithm for the PSO. So essentially here we're just going to look for solutions that satisfy the delay requirement. And once we find the ones that satisfy the delay requirement, we're going to select the one that has the best cost here, right? And so that's going to be our optimal allocation here. We compare this with a greedy heuristic that prioritizes high capacity nodes, and we show the result here. For the experimental setup, so here we went with a 25 node test bed. So we have one cloud server, two edge servers, and 22 INC-enabled P4 switches, right? So the numbers of users was set to 50. And we have essentially two scenarios. So a scenario where we have in-network computing and without in-network computing, and another experiment where we varied the numbers of Dieyes here. So in this figure here, when you see one here, it means that we are considering one digital assets. So if you see two here, it means we have two digital assets here. So PSO means that we're using the PSO algorithm. Greedy means we're using the greedy algorithm. So no INC means that this is a scenario where we didn't use in-network computing. INC means we activated the in-network capabilities of the network. Right. So here we can see the result is quite clear. So this is the threshold here, the 22 millisecond threshold that we had. So all the simulation that didn't have in-network computing failed this threshold. They went beyond this threshold, right? So the only one that were able to satisfy this threshold was the in-network computing scenario, right? Where in-network computing was activated, right? So we see that the PSO-based in-network computing is able to keep the latency less than 20 milliseconds, outperforming all the other methods. And the non-INC setups fail to meet this threshold in time. So this is the latency. And for the bandwidth here, for the refresh rate, I'm sorry. So here with the PSO approach here, we see that until 30 users, we were able to satisfy the 90 frame per second requirements, but after that, it went down. Which is normal because we have much more users and we have the same network topology. So here, until 30 users, we're able to satisfy it. For the other option, so where we didn't have in-network computing, actually, you see that we drop below 60 frames per second very quickly here. So this means from the end user perspective that we have a degraded viewing experience. So these are main results of the second work. So we're going to talk about the last work, which is an architectural proposal. So as you saw here, we just focus on the algorithm side. So we wanted to focus on the architectural side, mainly how to manage the in-network computing components, right? So for NFV, it's very simple. We have a standard that already exists, which is the manual framework that already exists that allows us to manage and orchestrate the VNF. So the simple objective is we want something like this for the in-network computing components, right? So what we did is a hybrid approach where we're going to be able to manage a service that has some parts NFV components and some part INC components, right? So what we did naturally was to extend the Mano framework that exists here, and we proposed a modified Mano, which will be able to manage both at the same time the in-network computing components and the NFV components here, right? So here, essentially, we added a mirror of VNF components. So here for the VNF catalog, we have just the INF catalog. For the VNF manager, we added an INF manager here. So in order to be able to simultaneously manage the two, so we have a new orchestrator. So we remove the NFV orchestrator and we put in a hybrid orchestrator, which will be called NFV-INC orchestrator or NIOP. Again, here the goal is to be able to manage both of these components at the same time here. So we implemented a prototype. So this prototype was developed by Farzaneh So she has now finished her master's. So essentially here we just made some changes to the open source manual here, so OSM. So here we continue to use Kubernetes for the NFV allocation, but for the P4 we changed it and added a plugin and changed the resource orchestrator to take into account the P4 plugin here. And we now have a P4 manager that we developed here for our use case. So here now we can have a service function chain, which will be composed of a mixture of VNF and network computing components here. So here, this was just a proof of concept. So here we tested a scenario. So here we have a scenario where you could have 4 VNF in the service, network service. So here we tested a network service where we had 3 VNF and 1 in-network computing component. So here we also changed it to 2 and 2 configuration, and until we have here 4 in-network computing components, right? So here the idea was just to test the deployment time. So this is just a first proof of concept implementation. So here we can see here with in-network computing components, we can actually decrease considerably the deployment time for the network services here, right? But as I said earlier, so whether we use in-network computing or VNF will depend on the types of function that you need to deploy here, right? So you won't be having, let's say, 4 network computing on a VNF chain by 7, right? So it will probably be a mixture of these 2. So for this work, this is the only main result that we have. We are continuing to test out this prototype, and we hope that we will have much more results in the coming months. Right. So for references, so these are some references that you can find in the literature. Of course, you can check our lab. We are doing a lot of work on in-network computing and the metaverse. Also, Manel is working on an extended version of the paper that we presented. So this time she will try to use reinforcement learning based approaches and see if we can have much better results than what we currently have here. So with that, thank you for your attention.
Si vous avez des questions, vous pouvez les poser en français, j'imagine.
Différents paramètres que la CHG doit apporter pour augmenter la bande passante, la latence et tout. Je vois que c'est la même chose que vous voulez faire ici avec les prototypes d'enfants. Et donc, je me demande, est-ce que ce n'est pas...
Non, en fait, on a dit ici, en fait, je pense que donc, certainement vous parlez de Box 6G, etc. Donc il y a plusieurs innovations qui vont exister pour la 6e génération. C'est juste que donc ce sont des enabling technologies, ce sont des technologies en fait qui vont permettre d'atteindre en fait ces buts-là. Okay. Nous, on considère que le network compute, ça va être une technologie de plus qu'on pourra utiliser. Donc ici, le but, ce n'est pas forcément pour ces technologies-là, ce n'est pas forcément d'économiser en termes de bande passante ou bien d'économiser en termes de latence. Donc là, ça va être par exemple pour de la bande passante, etc. Nous, notre objectif principalement, c'est de réduire la bande passante qui va être transmise donc, au niveau du réseau. Okay. Donc ici, au lieu de, au niveau donc, de la source, ici de la destination, au lieu de transmettre en fait tous ces données en fait jusqu'à la destination, jusqu'au serveur, on va commencer à faire en fait le processing au niveau donc, du réseau. En fait. Et ça va nous permettre de réduire en fait la bande passante qui va arriver ici au niveau de la destination, et puis la bande passante qui va retraverser en fait le données de la source. Donc, c'est plus en complément que quelque chose qui va en fait concurrencer les autres approches.
Oui. C'est l'enjeu de sécurité, vu qu'on déplace maintenant du computing dans le réseau plutôt que juste sur les serveurs, parce que les serveurs ont une puissance de calcul beaucoup plus importante pour la sécurité.
Donc, c'est l'une des raisons pour laquelle je dis que ce n'est pas toutes les fonctions qui vont être exécutables avec network computing. L'aspect de sécurité est un aspect très, très important. C'est juste que nous, on ne travaille pas au niveau sécurité, mais oui, c'est un point qui est très important, je pense.
Ouais. Pour l'aspect sécurité, en fait, j'ai l'impression que ça va dépendre beaucoup de qui va être en contrôle des deux. Parce que si tu distribues ton calcul à l'intérieur de ton réseau, puis une partie du réseau se trouve du côté dans l'infrastructure qui appartient à la compagnie qui est les serveurs, l'autre partie du réseau, c'est du côté dans l'infrastructure qui appartient du côté du client. Tant que tu n'as pas le entre les deux qui n'importe qui peut le contrôler, c'est pas très différent de networking présent.
Oui, mais même en fait, sécuriser juste un seul serveur, c'est beaucoup plus facile que sécuriser tout le réseau. En fait. Donc, c'est un point qui est pertinent, à mon avis. Donc là, c'est vraiment, on va regarder en fait quelles sont les tâches qui peuvent être exécutées sans vraiment ajouter en fait, des vulnérabilités. Donc, ces tâches-là, on va les exécuter avec network computing. Les autres tâches, on va continuer à utiliser les serveurs.
Yeah, so can you please elaborate more on the people plugin that you talked about, like what's the role of the people plugin and where it was integrated?
Yeah, so the P4 plugin was for the implementation side. So essentially, we just created our own program. So when we receive a request, so the resource orchestrator will decide, should this one be done on VNF or in-network computing? If it's done on in-network computing, then we're going to activate here some network components and say, okay, try to run this in-network computing component and execute. Essentially, that's
So here again, in that in-network computing, like the whole function is going to be programmable in people and it's going to be executed on the people.
Yes, that's the assumption.
Yeah, so now that the people switches have been like upgraded and we have separate functions for like the VNS and their original form, have you considered choosing that instead of here we don't need like the P4 plugin because we have separate functionality in the P4 where we can execute the VNS to their original form?
Yes, but here the goal is we want something that is hybrid, right? We want to manage this with a single framework, right? So we need to be able to manage the VNF and the INF at the same time with just one framework here. So instead of having the network computing this way and the VNF this way, so we want something that is combined here. So that's the goal of this.
So the administrator here is located at the level of the SDN.
The orchestrator, yes, essentially, yes. So here we didn't define it specifically, but here we can have the orchestrator maybe at a layer above, or maybe we can just, to simplify, just place it at the control plane.